Recording.
Welcome to this history of geometry class, which I have named Here's Looking at Euclid. Our objectives for today, we're going to understand the difference between like practical and theoretical geometry, and we're going to kind of follow a little bit of the history of geometry. We're going to meet some of the big players in geometry. And we're also going to understand the connections between the ancient Greek geometry and the geometry that we have today. So as far as like how far back geometry goes, if you look at practical geometry, it's prehistoric. Theoretical geometry, though, with the two-column, well, they weren't always two columns, but yeah, with the proofs, the formal proofs, that's about 2,600 years old. So before the time of Christ. And we still are making new discoveries in geometry. It is not a dead field. And I'll talk a little bit about some of the major strains of geometry in a little bit, but I want to make sure everybody understands that it's not this dead thing that it kind of gets presented as in school, because they give you these proofs, you got to learn these proofs, and everybody learns the exact same proofs, and I got to tell you, people have been learning the exact same proofs for 2,600 years. Okay, so you're not alone in thinking it's a little stale, but nevertheless, these are the foundations of what we study today as geometry. Unfortunately, you typically don't get to see that outside of high school, or in high school. You have to go to college and major in math to take classes like that. But I'm going to try and make that information more accessible in my future classes. Okay, so the name geometry comes from Greek root words meaning earth measure, geometria, geometria. Geometry was originally developed for like application stuff. So surveying, architecture, people want to build pyramids, they want to survey land, they want to do things like that. And of course, the ancient Greeks were big into philosophy. And so one of the areas they took that into was to try and figure out what the fundamental truths of the universe were. And they discovered geometry, the theoretical geometry. Okay. Most of what we teach in school today is geometry is the theoretical stuff. It's not the applied stuff. So let's look at the difference between that practical geometry and the theoretical geometry. Practical geometry is being able to use things for specific real world purposes. You don't have to understand the theory behind them to be able to do them. And I'll show you some examples of that in a bit. Contrast that with theoretical geometry, which means you're understanding the pure mathematics behind those practical situations. But you may not always be able to apply it to real world situations. Mathematics for mathematics' sake is done without any thought of application to real world situations. It typically takes about 100 to 200 years for mathematical ideas to filter into places like physics. What happens is the physicists are trying to solve a problem in the real world, and they turn to the mathematicians and say, hey, do you know anything that works like this? And they go, actually, I do. Semi-groups work like that. And they go, oh, okay. So yeah, theoretical mathematics is just for the sake of itself. It's like art for art's sake. Here's an example of the difference between practical geometry and theoretical geometry. So the illustration on the left is, it just demonstrates how the ancient Egyptians would make a right angle in surveying. They would have a rope that was knotted off in 12 equal segments, and they would just arrange it so it was 3 segments, 4 segments, and 5 segments, and they knew that that made a right angle. Theoretical geometry is knowing something like the Pythagorean theorem that 3 squared plus 4 squared equals 5 squared. That's the difference between practical and theoretical geometry in a nutshell. You don't have to know the Pythagorean theorem to take a rope with 12 equal segments. You just have to know that it works and that it makes the angle that you want. Does that make sense?
Yep, makes sense.
Okay. Here's another example of practical versus theoretical geometry. Some of you scribes out there are drooling right now at the illustration on the left. Okay, that's that's showing the construction of the trefoil. So you can actually construct these arches and things like that using, well, on paper it would be a ruler and compass, you know, and when you're talking about the scale of buildings, you're using, you know, lengths of rope or board, and you're rotating them around a central point, and scribing things with chalk and stuff like that. But you can learn how to do something like that without knowing why it works. Like, for example, you don't have to know that they're constructing, can you see my cursor? Can people see my cursor?
Yes, we can see your cursor.
So you don't have to know that connecting these 3 points would make an equilateral triangle in order to make this shape. You don't have to know that. Contrast that with the illustration on the right, the theoretical geometry. This is a geometric proof of the law of sines. What do we use the law of sines for? Well, we do use it to solve triangles, you know, to take any triangle, not just a right triangle, and figure out what the lengths of its sides and its angles are. But the proof here, this geometric proof, is showing that the law of sines is true by equating areas. And you really have, that gives you a deep appreciation. If you understand what it's saying, it gives you a deep appreciation of the law of sines, but it doesn't help you solve a triangle. Okay, last example. The ancient Egyptians were able to find the volume of a pyramid. They had formulas for that. And we have lots and lots of formulas that we use, and we teach them in math classes. You know, we teach that to find the area of a triangle, you take the base times the height and divide it in half, and things like that. Theoretical geometry is knowing that 2 cones equals a sphere. That's not real practical, but it does make eating a snow cone more fun, because the snow in the cone part at the bottom is the same volume as the snow in the hemisphere on top. So that does make it kind of fun, but it doesn't really add anything to your life to know that. Like, the snow cone doesn't taste any different when you know that while you're eating it. So the ancient Egyptians had some practical geometry knowledge. They did have the concept of seqed, which was the slope of the side of a pyramid. Now, they calculated it a little differently than we calculate slope. We do rise over run. The ancient Egyptians did it the way that high school students tend to want to do it, which is run over rise, okay? The equivalent trig function is the cotangent of an angle, but they weren't that theoretical. They just knew that it worked. They also knew that vertical angles should be congruent. Now, vertical angles is when you have 2 lines that cross like this, and then the angles on the opposite sides are congruent. So they knew that should be true, and that helped them to figure out whether lines were straight or coming at each other in the proper manner. They also could construct right angles, and they knew Pythagorean triples. That's not the same as knowing that a squared plus b squared equals c squared. They knew that 3 squared plus 4 squared equals 5 squared. They knew that 5 squared plus 12 squared equals 13 squared, but they didn't know that, like, 1 squared plus 2 squared is the square root of 5 squared. They didn't know that, okay? They're just whole numbers that worked for those Pythagorean triples. They knew those. They had a whole table of them. Ancient Egyptian mathematics loves tables. It's really kludgy compared to our streamlined stuff we have today. But yeah, they did know several Pythagorean triples, and they had whole tables of them. Let's just recall, if you've taken my other math class, then you've seen this information before. The Greek numeration system sucks. It's worse even than the Roman numerals. Okay, it's base 10, it's non-positional, they don't have a 0, and they use letters instead of numbers. And so if you wanted to say, 54, you'd write nu and delta. Obviously, that makes it a little difficult to tell the difference between words and numbers. They were big into numerology with that, but because you can't really do math with Greek numerals, they had to figure out a different approach if they wanted to do math today. So the way that they approached it was they approached it through geometry. Instead of a number, that they would add to another number, they would think of it as like a line segment, and they're placing it next to another line segment. For multiplication, that would be an area. They were calculating areas when they calculated multiplications. And so they had this whole system whereby they could do a geometric construction, and that was a proof of an algebraic equation. That was like the solution to an equation. So let me show you examples of that. So first we see they would make a length and just call that length 1. That's our unit for today. It can be a different length tomorrow, but today this is our unit. And then if you wanted to make 2, you would put 2 copies of that same unit next to each other in a straight line. That made 2. If you wanted to make 3, you'd put 3 copies of it. Okay, if you wanted to make the square of 2, you'd take a square, literally a square with that was 2 on each side. And you can actually represent quadratic equations this way. I've put an example here. And this concept is still in use today in the concept of algebra tiles. This is a manipulative that's used quite often to teach mathematics at like the high school and middle school level. And they use these algebra tiles to show people how to factor and things like that. It's a very hands-on manipulative. It's really great for people who are kinesthetic learners, or people that have to see something and they can't make that abstract leap for whatever reason. Maybe they're too young and their prefrontal cortex hasn't developed, whatever the reason, or they have a learning disability. These are great algebra tiles. But the basic idea is that if your unknown quantity is x, okay, x squared is a square that's x on a side. And if you wanted to represent x plus 2, you take that length x and then you add 2 units to it. And so if we wanted to multiply, say, x plus 2 by x plus 5, we would make a rectangle that's x plus 2 on one side and x plus 5 on the other side. And then we'd break it down into these 4 regions. This one's x squared. This one's these additional 5 times x. This one's the additional 2 times x. And then this one is 2 times 5, which is 10. And so when you add all that up, we would put it in our notation today, x squared plus 7x plus 10. But you can actually solve quadratic equations this way with a geometric diagram. It's not something, they don't commonly teach you in school how to solve equations like that. It's more of a new thing, the algebra tiles. But, because most of us who are, if you're my age or close to my age, you probably didn't learn that you actually can solve these things geometrically. Geometry was the province of triangle congruence. Another thing that became an issue with this method of constructing math problems is that not every right triangle can have rational numbers for sides. The ancient Egyptians had that whole table of Pythagorean triples, but as we've seen before, you can't always get nice whole numbers that make Pythagorean triples. Like, for example, this is actually a very common triangle that pops up in the construction of the regular polygon or regular pentagon. So this is a triangle that's side 1 and side 2. But then what's the length of this third side? Well, we know it to be the square root of 5. We can apply the Pythagorean theorem because we have the theoretical geometry necessary to find what that number is. But remember, the ancient Greeks did not have the number symbols that we have now. And so they knew that this was a length, and they knew that it was a real thing, okay, a real number, but they didn't know what length it was. And so there were processes they could go through to try and like make a fractional approximation to it. They did use that to approximate pi, because pi is also an irrational number. But they didn't really know what that length was. And they didn't know that pi was irrational either. There's a famous problem in geometry. It's called squaring the circle. And you may have heard this phrase before, because the phrase exists when people don't understand what the actual problem was, the original problem. But the original problem was to make a square that had the same area as a circle. In order to do that, you have to be able to, I think, take the square root of pi, if I'm not mistaken. Square roots are irrational. Pi is irrational, so the square root of pi is super irrational. but the Greeks couldn't construct that number because it was not one that they could construct. And so that's why we use the phrase squaring the circle to represent something that's impossible to do. It was much later proven to be completely impossible to construct. So the way that they would try to approximate this number, like square root of 5, would be to set up ratios of lengths and try to figure it out that way. And they could get kind of the equivalent of our decimal approximation, but they didn't conceive of this number as the square root of 5. So now that we have a little background on like the Greek approach to mathematics, let's meet some of the big players in geometry. Thales is considered to be the father of modern or theoretical geometry. He was the first one to use that in his philosophy. He learned about similar triangles, and he developed some theorems about circles and about triangles, and he was able to use his geometry in a practical way. He first learned about practical geometry in Egypt and brought that knowledge to Greece, but then he theoretized it. And he was able to successfully predict an eclipse as a result of that. I put Pythagoras in here, even though he really didn't do anything. His name is on the Pythagorean Theorem, but that theorem predates his birth. So it's doubtful that he actually discovered that theorem. What he is known for is being a freaky weirdo. He founded a vegetarian math commune that did not allow people to eat beans. In fact, the legend is that he died when his city was invaded, and he was running from the invading soldiers, and he ran to the edge of a field of lentils, and he would not go in because beans are yucky, and they killed him right there on the edge of the field because he wouldn't go hide in the field. He was not above killing people himself. There's a rumor that he had the guy who discovered irrational numbers killed because it conflicted with his teachings. His motto was "all is number," which is great, but yeah, it's not all number, as some of you may have already discovered. So I put him in there just for thoroughness because everybody wants to know about him. He's a really weird guy. Interesting, but weird. Also very influential. People, obviously thought that he was cool, and there was actually later, there's what is it, Margarita Philosophica? That's the one that shows him and Boethius going at it in a competition. Yeah, the medieval people really thought he was the stuff, but he was not the stuff. Eratosthenes of Cyrene is an interesting guy. He was able to successfully measure the circumference of the Earth. So that was a big discovery. People who are like, oh, everybody thought the world was flat before Columbus proved them wrong, is wrong. They knew the Earth was round at least that long ago. This is before the time of Christ. So yeah, people knew the Earth was round. And Eratosthenes is one of the reasons why. He also invented the Sieve of Eratosthenes, which is a process that you use to get to find prime numbers. You ever taken? I did this as a kid. I used to love to do this. Take the 100 grid, where you get all the numbers 1 to 100, and then you cross out the 1, and then you circle the 2, and then you cross out all the multiples of 2. And then you circle the 3 and you cross out all the multiples of 3, and then the 4 is gone already, so you circle 5 and you cross out all the multiples of 5. You keep doing that. That's called the Sieve of Eratosthenes. It's a method to find prime numbers. I was a weird kid, by the way. So here's how Eratosthenes discovered the size of the Earth. So there was a well in Syene in Egypt. It's now Aswan. And on the summer solstice, the sun would shine straight down this well. Okay, so he knew that the sun at that time was right over Syene. And then about 500 miles away in Alexandria, he saw that on the summer solstice, the sun cast a shadow. It didn't go straight up and down. It cast a shadow. So he used this And he assumed that the sun's rays were parallel. That's actually not true. The rays are not parallel, but from the distances that we're looking at, it's close enough for him to get a pretty good estimate. And from that, he was able to solve this triangle here. Find the measures of this arc here. So we knew that was 524 miles. We found the angle, because that's the same angle as this one right here. Okay. Using those parallel theorems that you learned in geometry, yeah, that's what that stuff was used for. He was able to find that he actually found it pretty accurately, although we're not entirely sure exactly how accurately he was, because he used a unit of measure called stadia, and nobody knows how long a stadium is. So anyway, but from what we know of other measurements that we've been able to kind of estimate what a stadium is, his estimate was actually pretty damn accurate, and especially for his time, and especially for a guy that couldn't do computations with numbers, that had to do it by geometry. So that's the peak of the Greek geometry knowledge. They were able to do things like that. So the big player, though, that I really want to introduce you to is Euclid. So Euclid was the author of the most famous geometry or any branch of mathematics textbooks in the world. It is still in use today. You can still go on Amazon and buy a copy of Euclid's Elements. I kid you not. Although you probably want to go online and get it if you're not really that interested, if you don't want to spend the money. He was a pretty prolific writer. He wrote a lot of books. The Elements itself has, I think, 13 books, if I remember correctly. Of course, by book, they mean scrolls, right? That's what it meant back then, was a papyrus scroll. Some of his works are lost. Of course, the Library of Alexandria burned, and then, a lot of stuff was lost. And we know that he wrote them because they've been referred to in other books that have survived, but we kind of have some idea of what's in them because of what other people did building on his works, but those particular works are gone. They're lost. We'll never find them. He also wrote on geometry. Besides geometry, he wrote on spherical trigonometry and optics. So spherical trigonometry, what that is it's the study of triangles on, say, the surface of the Earth. You can have a triangle on the surface of the Earth that has 3 90-degree angles. Those of you who've taken high school geometry are freaking out right about now. You're like, wait a minute, don't they have to add up to 180? 90 and 90 and 90 is not 180 on the surface of a sphere. They don't. And we'll talk about that in a bit. But you can imagine like a 90-degree angle at the North Pole, and then it goes down to the equator as the other side. You can have a triangle with 3 90-degree angles on the surface of a sphere. So trigonometry works a little different on the surface of a sphere, and he wrote about that too. So Euclid's Elements, here's what it covers: plane geometry, solid geometry, so that's 2D and 3D, what we now call Euclidean geometry. It talks about incommensurable quantities, so that's your irrational numbers, things like that. Geometric constructions, so like how do you find a line that's tangent to 2 circles at the same time? I've actually had my geometry students do that one from Euclid's Elements. He also talked about number theory, and this comes up in, I actually learned about the Euclidean algorithm in my abstract algebra class as a math major in college, but it's a basic idea that it's an algorithm that you can follow that will help you get the least common multiple of 2 numbers, least common factor of 2 numbers, which helps you find the least common multiple. And I've showed it to my students, they're like, that's easy. I'm like, yeah. It's not that hard to follow, but it's not the topic for tonight. So here's one of the more basic problems from Euclid's Elements. I thought you might like to actually see this problem. So the problem says it is required to construct an equilateral triangle on the straight line. Okay, so it gives you a straight line, AB, okay? He says, first, describe the circle BCD with center A and radius AB. So you set your compass to this length and you make this circle right here, okay? And then he says, again, describe the circle ACE with center B, and wait, center A and radius. Okay, so he has this circle first and then that circle, my bad. Okay, so this will prove that this side, AB, is the same as this side, AC, because they're both radii of a circle. And then that's the same as this side, because this side is the same as that one, because they're both, again, radii of the same circle. And so because things that are equal to each other, or things that are equal to the same thing are equal to each other, therefore, this is an equilateral triangle. So he's showing you like, he's kind of integrating some of this practical geometry and this theoretical geometry. So he's showing you how to do the construction, but then he's showing you why the construction proves that that's an equilateral triangle. Does that make sense? That's what he's showing you in this sample problem that I've put forth from the elements. This was a shorter one. The construction to do the line tangent to two different circles that don't touch each other was actually very involved. There's actually 4 lines that do that. Topic for another day. Another big player in the history of geometry was Theon of Alexandria. For those of you who are familiar with the story of Hypatia and the burning of the Library of Alexandria, this is her dad. He was the one that arranged and kind of edited elements, and he tried to make some corrections to things he thought were wrong. He also published commentaries, and this is one of the ways that we have the knowledge that Euclid had written these texts that are now lost, because he made commentaries on them. He also wrote a treatise on the astrolabe, but it too is lost. So that's kind of my little hobby horse there, the astrolabes. Like one of these days I'm making one, but so I'm kind of sad that his treatise has been lost. But anyway, so he was a kind of a big player in that. These papyrus scrolls don't last. They don't last more than a couple hundred years. And so if you want to keep a text going, it has to be recopied every couple hundred years. So that's what Theon was doing, was kind of recopying the elements and kind of editing it a little bit, putting in his own little commentary and stuff like that. He was basically republishing the ancient textbook. So here are some texts of the elements that come from different places, different times. This is the earliest, the one on the left, the Vatican Euclid. This is the earliest known text of the elements that still exists today.
You know, those are just pretty scrolls. They're just gorgeous. The whole look of the page.
Yeah, I picked pretty ones. Top illustration here is the classic proof of the Pythagorean theorem. This particular proof, there's hundreds of proofs of the Pythagorean theorem, but this one is called the bride's chair. And then you can see he's got an illustration here of a lune, which is what's left after you take a half circle out of a half circle, with some various circles tangent to the 2 inner and outer circles. That would be a very difficult construction, but it can be done. This one is written in Greek. This one is also written in Greek. It comes from Byzantium. And you can see the pretty illustration there. Okay, and then this one on the right, that's an edition in Hebrew from the 14th century. And you can see that people tend to write in the margins and make notes on the textbook. People do that today, and I know that a lot of us were raised that you don't write in a textbook, damn it. But people have been writing in textbooks for many, many years. Thank you very much, and they keep going. So if you've taken an algebra, like that Algebra 1 geometry, Algebra 2 sequence in high school, you may have been wondering, like, why the hell do we pause algebra and take geometry in the middle? Well, what it really is, if you keep going on that sequence, is you get Algebra 1, and then you get geometry. And then you get Algebra 2 and trigonometry. And then on top of that 4-block foundation, you build your calculus, okay? So trigonometry is like a development of geometry. And it's a specific branch of geometry that deals with triangles and with the ratios called the trigonometric functions, okay, that we today call that. Trigonometry, as we know it today, was invented in India. We tend to, think of the ancient Greeks as like big trigonometers, but they actually were more into the geometry side of this. India got into the trig functions. So they created these trig tables, and they also invented infinite series of the type that we now call Maclaurin series, because I think there's a rule somewhere that everything in mathematics has to be named after a dead white guy, not the person who actually invented it. But but yeah, they were able to like use infinite series to expand some of these trig functions and get really accurate tables. And you can see one of these tables here. And this, we're talking like 7th century to 9th century as our time frame for this. Yeah, that's how long ago they were doing this. They did it a little differently than we do. Like we think of the trig functions as sine, cosine, tangent, and then if you've expanded and taken trigonometry, you'll know cosine, or you'll know cotangent, secant, and cosecant. But they didn't do sine as we do it. They did sine of what we would call sine of 2 theta. The thing that they called the sine function was called ja, or bowstring, because if you actually draw out the diagram, it looks like the string of a bow. And this got mistranslated. It was mistaken for a similar sounding word that means bay, like a bay that you would ride a ship into. And because of that, when it got translated into Latin, that word got translated into sinus, which means a bay in Latin. And so that's where we get our word sine. Kind of a long, history of translational inaccuracies, but there it is. So the way that Euclid's Elements came down to the present day, because, Library of Alexandria burns, what are you going to do now? Well, copies of Euclid's Elements existed all over the place. And when the Arab world began to rise, the Caliph sent scholars to Byzantium and all over the place. They sent them to India. They sent them everywhere looking for texts. It's texts on science and mathematics and medicine. They were looking for those things so that they could build their knowledge, have them translated and build their knowledge. So this is actually the way that we get some of these ancient manuscripts, is only through the Arabic versions of them, translations of them. I've got here some very pretty Arabic manuscripts of Euclid's Elements for your drooling and perusal, showing how you construct certain things. So the knowledge came to Europe through the Arab world, and specifically through a couple of major routes. One of them was through the Crusades. People went down to the Arab world for the Crusades and came back with stuff, and sometimes that stuff included books. The other main route was through Spain. Spain being at that time partially ruled by Muslims and partially ruled by Christians. And so there was a lot of intermixing And people would go to college in Spain. I think I've mentioned in my previous class, Pope Sylvester, or the man who became Pope Sylvester, had studied in Cordoba, I think it was. He went to college in Cordoba and found those weird Arabic numerals, the ones that they keep trying to teach our kids these days. Anyway, he found these Arabic numerals, and he thought they were so cool, and he brought them back and wanted everybody to use them, and they were just like, those are Satan's numerals. But yeah, those are the two main routes by which the information came through the Arabic translations to Europe. And geometry then became considered one of the 7 liberal arts. The 7 liberal arts, and we still refer today to like a liberal arts education, meaning somebody who's well-rounded, but the original 7 were dialectic, which is logic, rhetoric, which is like how do you construct a persuasive argument, grammar, and then the quadrivium was arithmetic, geometry, astronomy, and music. So these were considered the components of a good education, and we still learn these today. I mean, when I taught a class this summer, mundanely, it's called Math for Liberal Arts, and we covered dialectic, rhetoric, arithmetic. That's pretty much what we covered in that whole class. So yeah, we covered liberal arts. When I teach the full version of it, that's not during the summer, we do all 7 liberal arts through the lens of mathematics. So Euclid's Elements is still in use today. You can still find it at bookstores. You can go on Amazon and search it up and find it and order it and have it shipped to your house. It has been continuously in print, if you want to count manuscripts as print, longer than the Bible. Because the Bible was put together in like the 300s AD in its current form. I mean, some of the texts existed before that, but Euclid's Elements existed before Christ was born. So yeah, this book is old. That's why it seems so stale. But we still teach in modern geometry classes the exact same theorems and proofs that are in Euclid's Elements. We just say them a little differently.
We actually, in my classes in university, we still use that book for stuff. It's crazy. I have a copy downstairs.
Yep. Yeah, it's still in use. I taught, most recently, I taught a homeschool geometry course to my daughter and her friend out of Euclid's Elements. So I had mentioned Euclidean geometry. Then you're thinking, is there any other kind? Well, yes, actually there is. So Euclid's work has not been without controversy. There have been a lot of people have questioned certain aspects of it over the years. And one of the ones that was questioned most recently is Euclid's 5th postulate. So if you look at the Elements, he lays out the axioms, which are the things he's just going to assume to be true, and postulates, which are things that might be true, but he's really not as confident in them as in his axioms being true. His 5th postulate in particular has been the source of controversy over many, many, many years. It's called the parallel postulate. And what it says is that if you have a line and you have a point that's not on that line, then you can draw one parallel line through that point. And everyone's like, 1, why 1? Why not 0? Why not 2? Why not 17? And so it actually turns out that if you make it only 1, you get what's called Euclidean or plane geometry, flat surface geometry. But if you make it 0, if you say that if you're given a line and you're given a point and you can't draw a parallel line to this line through that point, then you get what's called spherical geometry. It's the geometry that lets you have a triangle with 3 90-degree angles on the surface of the Earth. And if you let it be more than 1, then you get what's called hyperbolic geometry. Hyperbolic geometry actually turns out to be the geometry of the universe because we've been able to measure it, and it's hyperbolic, very mildly so, but hyperbolic. And so that's led to a whole other branch of non-Euclidean geometry opening up. And there are all kinds of different weird geometries out there. There's like 3-point geometry where there's only 3 points in the entire world. And then you see what you can do with that. You can set any particular number of points in the world that you want and then prove things about it. But one of the beautiful things that's come out of the discovery of hyperbolic geometry is the art of M.C. Escher. And so this illustration I've put here is his work, Angels and Devils. It is drawn on a representation of the hyperbolic plane, which is called the Poincaré disk model. So the way that it works is that a straight line in this model, because the entire universe is now contained in this disk, and it's got a hyperbolic local geometry. So the way that you have a straight line is you actually have an arc. An arc is a straight line. It has to be a piece of a circle that's tangent, or that meets the edge circle at right angles. And so you can have this is a straight line here, but then this is also a straight line. Okay, and you can have a 0, 0, 0 degree triangle in hyperbolic geometry. All of your triangles have to add up to less than 180 degrees, and so you can have a 0, 0, 0 triangle. It's kind of freaky, but true. So that's the impact. Euclid is still having an impact today. People are still questioning his work, still looking at what he does. Still, he's still relevant 2,300 years after he wrote a textbook. We can all only wish for such fame. Any questions?
I typed one.
What's that?
I typed one in the chat.
It's hang on. Let me see the chat then. Okay, Diophantus of Alexandria. Yeah, so Diophantine equations are actually not taught today in high school, but they can be. Diophantine equations, for those who aren't familiar, are the ones that they have 2 variables, but only 1 equation. You're used to seeing 2 equations, 2 variables, but this is 1 equation, 2 variables. And they actually have multiple solutions, and there's a way that you can generate the solutions if you know a little number theory. But he of course wouldn't have approached it as an equation with solutions. He would have approached it as geometry. Is that?
No, just wondering if you knew anything about it, because I have the book and it's interesting, but yeah.
Yeah, no, that's about all I know about it at the moment. I can research it. Questions?
I don't have a question, but I do have a weird comment about Pythagoras and his beans.
Yeah.
So as part of my mosquito class, I was looking at Fauvism, which is it's the response to G6-PDD and how it works with the red blood cells. And one of the triggers for it in the Mediterranean population is eating fava beans.
Oh.
And so actually eating fava beans can do weird things to you if you happen to be of Mediterranean descent. Just
well, I wonder if he had it then.
I don't know. I just more of there may have been a reason he didn't like beans, but obviously not going through a field of lentils is a little bit excessive. And yeah, I know.
Yeah, he was kind of the Trump of ancient Greek mathematics.
But thank you for this. This is awesome. Thanks.
No problem. Well, I hope everybody had a good time and learned some stuff. And,
thank you so much. Geometry is like my math happy place. So thank you.
Well, you're gonna like my next class then. I'm working on one on the 17 wallpaper symmetries of the Alhambra. So
I hope you're gonna do the other class you offered as well, because that's the one that I really wanted.
I'm trying to remember which one that was because my brain is fried today. Oh, I think that was Like practical constructions, was it?
It was, yeah, it was